This is a production of the Chemical Education Material Study.
Iron reacts slowly with the oxygen and water in air. We call it rusting, much more rapid in the ocean. Natural gas can also react slowly, but speeds up when ignited. What factors at the molecular level control rates of reaction? Clearly, understanding how to control chemical reactions is a subject of both scientific interest and great practical importance. Some of the factors involving the control of chemical reactions can be illustrated in a relatively simple reaction, that of H2 plus Cl2 giving 2HCl. This reaction can occur at varying rates. At room conditions, the reaction rate is very slow. If the mixture is exposed to a flash of laser light, the mixture explodes to give HCl. Heating or sparking also sets off the explosion. Here is the net reaction, but it does not happen just because H2 and Cl2 molecules collide. What does happen at the molecular level? This animation represents chlorine molecules moving around at room temperature. As the molecules collide, their electron shells repel one another, so they rebound. Now the temperature has been raised. The molecules move faster. The more energetic collisions begin to break the molecules into free atoms. Similarly, since chlorine is a colored gas, it can absorb visible light, and a single low-energy photon may also break a chlorine molecule into two free atoms. When a free chlorine atom collides with a hydrogen molecule, a hydrogen atom is released and HCl forms. The collision formed a structure called an activated complex. This H2Cl complex dissociates into a molecule of HCl and a free atom of hydrogen. Each hydrogen atom can strike a chlorine molecule to produce hydrogen chloride and chlorine atom. The first step is Cl plus H2 gives ClH2, which gives HCl plus H. The second step is H plus Cl2 gives HCl2, which gives HCl plus Cl. The net reaction is the sum of the two steps. H2 plus Cl2 gives 2HCl, with the H atoms and Cl atoms maintaining the chain into millions of repeating two-step processes. Note that each step has its own activated complex. The net effect is that the reaction proceeds in this chain fashion, producing more and more hydrogen chloride molecules and leaving fewer and fewer hydrogen and chlorine molecules. The chain is broken when two free chlorine atoms simultaneously strike a third body, which absorbs some of their collision energy, so the atoms do not bounce. They stay bonded as a chlorine molecule. If the total collision energy can form the activated complex, the reaction may occur. Otherwise, rebound occurs. This graph illustrates the energy changes. The vertical axis shows the potential energy. The horizontal axis, called the reaction coordinate, indicates the changing positions of the molecules or atoms during reaction. This point will indicate the energy as position changes. Now, using slower motion, let us look at a reaction between a hydrogen atom and a chlorine molecule. As the reactants approach each other, the point moves to the right, and we see that the velocities begin to decrease as the kinetic energy is changed into potential energy. Stopping the action, we observe that this collision has enough energy, called activation energy, for the system to reach a kind of changeover point. Here, the colliding atom and molecule are at the point of highest potential energy. They have formed the activated complex. The activated complex has definite bond lengths and bond angles, and enough energy to come apart as reaction proceeds. Once the system has passed this point, the reaction is quite certain to be completed. Now, watch the reaction again without interruption. In contrast, if the reactants do not have sufficient energy, they collide and rebound. The system reverts to its former state. The potential energy barrier for each type of reaction is different. This is the general shape of the barrier for the reaction between a hydrogen atom and a chlorine molecule, while for the reaction between a hydrogen molecule and a chlorine atom, this is the general shape. In nature, relatively few reactions take place between atoms and molecules. Most reactions occur between molecules. A reaction of two diatomic gases, X2 and Y2, to give 2XY, can provide a simple hypothetical example of such a reaction. With a high activation energy, most molecules would not collide with enough energy to react. But if they do react, they might first combine to form this activated complex and then split into two identical molecules of XY. Here is a possible potential energy curve for such a reaction. Compared to the potential energy curve for the reaction between a hydrogen atom and a chlorine molecule previously seen, we note that this activation energy peak is much higher. More bond rearrangement occurs. Again, you see that the reactants must have considerable energy in order to surmount the potential energy barrier and react. Only a very few collisions, such as this one, result in a reaction. The overall rate of reaction is slow. The height of the potential energy barrier varies with the orientation of the molecules on collision. In a favorable collision, such as this, the reaction proceeds through a symmetrical activated complex in which this XY distance is equal to this, and this XY distance is equal to this. The height of the potential energy barrier would then be the lowest possible for this reaction. For less favorably oriented collisions, a higher barrier is encountered. Suppose the molecules collide at an angle such as this. The less symmetrical activated complex has a higher activation energy, and the molecules are less likely to react. A reaction, and its reverse, may take place at the same time. While X2 and Y2 molecules are reacting in a forward direction to yield XY, some XY molecules react in the reverse direction to yield X2 and Y2. The motion of the point from left to right on the potential energy curve represents the forward reaction. Its motion from right to left indicates the reverse reaction. In general, the height of the potential barrier in the forward direction differs from that in the reverse direction. For this reaction between X2 and Y2 molecules, the height is smaller for the forward reaction. But for many other reactions, such as that between the hydrogen molecule and the chlorine atom, the height of the barrier is smaller for the reverse reaction. And in the reaction between the hydrogen atom and the chlorine molecule, the height of the barrier is much greater in the reverse reaction. Although the reverse reaction does occur, it requires much more energy, and a considerably greater proportion of the collisions will be ineffective, like this one, as compared with those of the forward reaction. If we begin with a mixture of X2 and Y2 gases, initially only the forward reaction producing XY occurs, because as yet there is not a sufficient amount of XY present for the reverse reaction to be appreciable. However, as more XY molecules form, the rates of the forward and reverse reactions become equal. Dynamic equilibrium has been established. Much reaction occurs, but no net change in the amount of any substance. Now observe that here, the heights of the potential energy barrier for both forward and reverse reactions are nearly equal. Hence, the energy required for going in each direction is almost the same, and the amounts of the three substances at equilibrium would be nearly the same. For the hydrogen and chlorine reactions, the forward barriers are much the lower, so the reaction goes almost completely to hydrogen chloride. Only minute amounts of hydrogen and chlorine remain at equilibrium. The frequency of collisions between pairs of molecules increases with the product of their concentrations. Therefore, reaction rates in gases are strongly influenced by the partial pressures of the molecular species involved in forming the activated complex. Reaction rates are also affected by change of temperature, because the chance of forming the activated complex varies with molecular kinetic energies. At lower temperatures, average molecular kinetic energies are low. Raising the temperature increases molecular energies and rates of reaction. It becomes more likely that the energy barrier will be crossed. Another highly effective method of increasing a reaction rate is to add a catalyst. The catalyst forms a new activated complex with one or more of the reactants, usually with a much lower activation energy. The rate increases. Living systems use catalysts, called enzymes, to regulate the rates of countless biochemical processes. The isolation of enzymes and the synthesis of new catalysts are major areas of chemical research. Much equipment in chemistry is used to determine concentrations, pressures, temperatures, and radiation levels affecting rates of reactions. Even athletes warm up to increase their heart rates and their performance. You probably do also.